Good evening, class. We are looking at exam 2 review, chapter 3, differentiation rules from 3.1 to 3.8. Here, section 3.6, derivatives of the logarithmic functions. So to start with that, when y equals ln x, what is its derivative? Well, we don't know that. However, we do know that the exponential format is e to the power of y equals x. We are going to differentiate this implicitly with respect to x. Clearly, the right side, the derivative becomes 1. The left side, any exponential, the answer is itself. And remember, y acts like g of x. So e to the power of g of x is e to the power of g of x times g prime. So e to the power of y is e to the power of y times y prime. To find y prime, you divide by e to the power of y. And of course, you can replace it with x. So we just proved if y is ln x, the derivative is 1 over x, meaning all you have to do, write the reciprocal of the argument. So if you have x, it becomes 1 over x. Needless to say, the reason we use a absolute value because of the limitation on the domain of a natural log, which is 0 to infinity. So if you don't want to write that, you have to write x is larger than 0. If it's ln of g of x, in the same token, you flip over g of x. And then the reason you multiply by g prime is the chain rule. Remember, u is normally considered a function of x. So if you write d dx of ln u, u is a function of x when we write d dx, of course. So you flip this over 1 over u times the u dx. This is the chain rule. In other words, this and this are identical. U is positive, U can't be 0. As long as you write U is positive, obviously, you can't be 0. You don't need to write that, but I want to emphasize that. That's why I put that. So if we are dealing with logarithmic functions and the derivative of that, that means we should be very comfortable with logs and the properties, and that's the assumption of this course. But I'm going to quickly give you the synopsis of that. It's important to understand when you're dealing with log, the base must be positive, can't be 1. And when we say y is log x base b, it is equivalent to say x is b to the power of y. In other words, in both cases, y is the exponent. So log is simply the exponent. That's all. So in both cases, the exponent is the same thing as y, the base is the same thing as b, and x in this case is called the argument, in this case is the result. Okay. Now, to understand this, I'm going to set up this arrow and just follow that. B to the power of y is x. So in the case of a general case where the base is any number, as long as it falls in this category, ultimately positive and can't be 1, then it creates the 7 properties as follows. Log 1 base b is 0, log b base b is 1, log b to the power of x of base b equals x. Those 3 class, just follow this arrow. B to the power of 0 is 1, b to the power of 1 is b, b to the power of x is x. These 2 refer to the fact that exponential functions and logarithmic functions are inverse functions. And these are more properties. This is called the product rule. Log base b of xy is log x plus log y, both of them base b. Log x over y is log x minus log y, all of them base b. This is called the quotient rule. Log of x to the power of n is n log of x, both of them have the same base. In other words, the exponent becomes the coefficient. Now, when the base is 10, don't write it. Y equals log x means 10 to the power of y equals x. And we can see the transition, and I hope everybody is okay with that. Basically, you lose the base b and you put log. When the base is e, you change it to ln. That means natural log, which means e to the power of y must be x, and it gives us those properties. Because the two functions are inverse of each other, they are symmetric with respect to the line y equals x. This is known as the change of base formula. Log x base b is log x over log b with any base, for example, a in general. What would we use here? Common log. Over here, natural log. You can use any of them for the sake of calculation. And notice in this graph, what does this say? I'm going to start with the red one. The red one refers to this point. The x coordinate is located at 1, 0. That's the meaning. ln x is negative for x between 0 and 1. So it refers to this branch. As you can see, when x is here, this one shows the y coordinate. If we go this way, then the graph shows that ln x is larger here. Anyways, it's important to know the graph of all basic functions, okay? And I hope everybody knows that. So let's move on and look at examples, again, reminding you of the formula for the differentiation. All right, we want to differentiate y equals ln of sine theta. We are going to follow this formula, and we're going to flip this over. We get 1 over sine theta. Then we need the derivative, g prime of x. That means we need the derivative of sine, which becomes cosine. Now we should know cosine over sine is cotangent theta. I've gone over that concept before as far as trigonometric identities are concerned. I hope everybody remembers them. Cosine theta over sine theta equals cotangent theta. Reminding you of what we have done before, it is using the quotient rule. So we're going to write this as f over g and go with this. So f prime is just the numerator times g, the denominator, minus g prime, the derivative of the denominator, is this part, minus e to the power of x. So this negative sign is here, and this one is g prime times f, which is e to the power of x. And you just write the denominator in a parentheses and square it. What we are looking at here, everybody, is as follows. F prime g minus g prime f. So all we have to do is simplify this. And to do so, we are going to distribute. This gives us e to the power of x. This gives us e to the power of x times e to the power of x, which is e to the power of 2x. So minus e to the power of 2x. This one gives us plus e to the power of 2x. So these two cancel each other. And the numerator has only e to the power of x. The final answer, y prime, is e to the power of x over 1 minus e to the power of x quantity squared. Y equals ln x cubed. There are two ways to do that. I'm going to look at it both ways. First, just imagine this is g of x, and again, we are using this one. So flip it over. 1 over x cubed. 1 over g of x. 1 over x cubed. Then g prime of x, the derivative is 3x squared. And obviously this, we'll have a final answer of 3 over x. And we're done. But what do I mean by the second method? Second method is to decompose this by putting the 3 in front first. This is the power rule. And now when you differentiate it, it's just 3 times the derivative of ln x, which is simply 1 over x. And you get 3 over x. By the way, anytime ln x is given, the assumption is it's a proper way of writing it. X must be larger than 0, okay? So what's the difference? For a case like this, makes no difference. The question is simple enough that either way we can handle it. However, the more complicated the argument of log, the better to decompose it. So as this gets complicated, we should follow the properties of logs. Now, what about y equals log base 3 of x? So to do that, we haven't done that. We've done the case where the base was e. As you recall, with the exponential, the same thing. We had to use some sort of a property to make a decision. So we are going to use the change of base formula and write this as ln x over ln b, which means 1 over ln b times ln x. Why do I separate them in this fashion? I want to emphasize that this is just a number, everybody. ln b, when we write it as ln b, it's an exact answer. You can do the approximation. So this is a number times ln x, and we know the derivative of that is 1 over x. So this one becomes 1 over x. This remains unchanged because it's a number, and we rewrite it. So we are going to do the same thing here. But before we do that, we are going to decompose that by writing this. Remember, you have to take the derivative of that. To make it easy, you write it as x to the power of 1/2, and you use number 7, the power rule, and you put the 1/2 in front. So we used number 7. That's why I put the number so I can refer back and forth. This is the power rule, everybody. So now we are going to differentiate. So y prime is the number in front remains 1/2. We're dealing with a log which is completely decomposed. Therefore, 1 over that, so 1 over x. However, the base is something other than e, and we need 1 over ln b, so we need 1 over ln 3. We put them together, and we write it as 1 over 2x ln 3. Make sure you put the 2x on the left. On the right, it may get mixed up with number 3. And that's it. So that's how you do the differentiation of log when the base is no longer e. What about this case? Again, reminding you that when we have a log, first we write, in order to differentiate that, we write the reciprocal of the argument, so 1 over f of x. Then by the chain rule times f prime of x. And then because the base is not e, by the change of base formula, 1 over ln b. And then we rewrite it. This is rewriting the idea. So in this case, we can decompose it further. So 1 over f of x. So this part is 1 over x squared plus 1. 1 over f of x. Then f prime of x, differentiate this. 2x. The base is not e, 1 over ln b, so 1 over ln 5. The base is number 5. So don't mix it up with here. It had a different base, 1 over ln 5. You're done. You rewrite it. Obviously, 2x is in the numerator. The rest is in the denominator. And you put x squared plus 1. And then in a parenthesis, meaning you're multiplying by ln 5. ln 5x over x squared plus 5. How do we differentiate that? First, we are going to decompose it. Why do we do that? Because if we don't, we have to flip this over, which is not too bad. Then we have to differentiate this using the quotient rule. We don't want that. So this is ln. I'm going to do this in 2 steps, although it can be done in 1. ln of the top minus ln of the bottom. So I used number 6, which is called the quotient rule. Then for this part, ln of 5x, I'm going to use number 5, the product rule. ln of 5 plus ln of x. Now, when you do decomposition, you want to decompose it completely. It makes it easier. So ln 5 is a number, everybody, and the answer is 0. ln 5 is a number, the answer is 0. ln x is 1 over x. But what about ln of x squared plus 5 minus, flip this over, and for this one, I'm going to use this one, everybody. So for this one, I'm going to use this one. Flip it over. The negative sign remains. Flip it over. Minus 1 over x squared plus 5 times the derivative of the argument, 2x. And I want to box that. I want to make a point. This is done as far as calculus is concerned. So algebra, algebra, more algebra. So there is only one step of calculus. That's why I keep saying calculus is easy. All right. Now, how do you deal with that? You need to take a common denominator between the two, which means it's x times x squared plus 5. Then what is the numerator? 1 times x squared plus 5 for this guy, minus 2x times x for the second one. I'm sure times x. I'm showing you exactly how to do this LCD and coming up with the answer, elementary algebra. And so we are going to simplify the numerator. This is x squared plus 5 minus 2x squared. These two, we can combine. And we get to the final answer, minus x squared plus 5. The denominator remains unchanged, x times x squared plus 5. The next one, g of x is log of 9 minus x cubed to the power of 4. So what do we do now? Again, I highly recommend you simplify the log, which simply put means decompose the log completely, which means in this case, I'm going to use, let me erase my work. I'm going to use number 7, everybody. The power rule. And I'm going to put 4 in front. This is using the power rule. And now I'm going to do calculus. So I keep the 4. So g prime of x is 4. Now I deal with the log. I will flip this over. So 1 over the argument of log 9 minus x cubed. Then I need the derivative of the argument by the chain rule, and that is negative 3x squared. Finally, I look at the base and I say, okay, the base is missing. That means the base is 10 because it's log. It's not E1 over ln 10. And that's the last piece that I need. And to put them together now, I rewrite it as follows. Y prime is 4 and negative 3x squared are at top, so negative 12x squared, everything is at the bottom. 9 minus x cubed times ln 10, and I keep this in front because if you put it after 10, it can be confusing because it's not part of the log, so you want to make sure you keep it outside. We are going to move on, everybody. Just want to make sure that everybody is okay with this. A quick recap. First, we put the 4 in front. That's number 7, algebra. Then we go to do the differentiation calculus. 1 over, so the 4 remains. So 1 over f of x, 1 over the argument 9 minus x cubed, times f prime of x, the derivative of that is negative 3x squared, times 1 over ln of the base. The base is 10, 1 over ln 10, and then obviously you put it together so you can see what we have here. So it's a pretty straightforward class. And so we are going to move on. All right. What happens in this case? Again, the same thing. We notice we have this part is a natural log. If we want to differentiate this part by itself, of course, we carry the 1/2, it's a number. But what happens here is that you have to flip this over and differentiate it using the quotient rule. It becomes a messy, and normally students don't come up with the correct answer. So what is the best course of action? Very simple. All you have to do, decompose this part, and to do so, you use number 6, the quotient rule. So 1/2 remains. ln of the top, 1 plus x, minus ln of the bottom, 1 minus x. So that's your first step, everybody. Now we are ready to move on with the next. To differentiate, first we keep the number 1/2. So we say y prime is 1/2. Then we work on this piece. That means flip it over, 1 over 1 plus x, times its derivative, which is 1, minus, now the derivative of this part, flip it over, 1 over 1 minus x, and then the derivative of this one is -1. And again, let me put an asterisk and show you that this is the end of the story. As far as calculus goes, everything else is algebra, everybody. So please understand that the first one, 1/2 remains the same. Inside the brackets, the LCD, the least common denominator, is the product of 1 plus x and 1 minus x. So this part class refers to this one, okay? So this has to be up here because minus and minus makes it plus. So we have this one and this one. So this one is 1 times 1 minus x. And this one, again, negative and negative makes it positive, 1 over 1 minus x, 1. So let me put that at top here so you see what I mean. This class should be up here. In other words, 1 over 1 minus x plus sign. What I wanted to emphasize is that this negative and this negative, they result in positive. So plus 1 times 1 plus x. That's what I meant to do. All right, so the next thing is to simplify what we have. And what we have right now is one use a different color. What color do you want to use here? Let's use a green. So over here, we have 1 minus x. Over here, we have 1 plus x. Obviously, these two cancel each other, and we get 2, and the 2 cancels out the 1/2. So the numerator is 1. What is the denominator? The product of these two, or 1 minus x squared. So a quick recap, everybody. What do we have here? We have natural log that must be decomposed, because if we don't decompose it, we have to write the reciprocal of this and multiply by the derivative of that, which require multiply by the methodology, which is using the quotient rule. So flip it over and then take the derivative of this using the quotient rule. You don't want to go that route. So you decompose this using number 6, the quotient rule. So it becomes ready for differentiation. 1/2 remains. This one becomes 1 over 1 plus x times 1. This one becomes 1 minus 1 over 1 minus x times -1. And after that, it's all algebra to put it together accordingly. Let's try this one. What I want you to notice is this. ln of 5x, we're going to call this g of x. And we are going to use this. So the very first thing is 1 over g of x. So 1 over ln of 5x. Then we need g prime, which means now take the derivative of this expression. Go ahead, Thomas. You have a question regarding what we have done?
Yeah, sorry. Can you explain to me how did you get 1 over ln on 5x?
Okay, let's go over it one more time. ln of this expression, which is ln of 5x, is called g of x. Look at this one. What is the derivative of ln of g of x? 1 over g of x. So 1 over this expression, 1 over ln of 5x.
Thank you.
According to the
I got it.
logarithmic properties when we differentiate. The next one. Now we need g prime. What is the derivative of ln of 5x? We apply this rule again. But this time, let me just erase everything. And this time, you're dealing with ln of 5x, where 5x is your g function. So 1 over 5x times g prime, the derivative of 5x, which is 5. So in short, In short, try this 2 times. Once on the argument, and again, you can literally change this to ln of g of x. Again, I'm going to write it. Just write this as ln of g of x, which makes this one g of x, and makes it 1 over ln of g of x, which is 1 over ln of 5. 1 over g of x, which is 1 over ln of 5x, and then ln of 5x itself, here's the derivative. Now, you drop the factor of 5 from the top and the bottom, the numerator becomes 1, and the denominator is ln of 5x times x. We put the x in front for a simple reason, everybody. The reason we put it in front, we don't want anybody to think it's ln of 5x times x, which means 5x squared. I'm going to recap this question to make sure everybody's comfortable with that. One more time. How do you differentiate this? In this case, the argument of natural log itself is a natural log. So this natural log of 5x entirely is the argument for this ln, so 1 over that, 1 over ln of 5x. Now take the derivative of ln of 5x, which is 1 over 5x times 5. We want to find the equation of a tangent line for y equals x squared ln x at 1, 0. And as you recall, to find an equation of a tangent line, you need two things. You need a pair. It's given. You need the slope. You have to calculate. The way you calculate it, you notice is the product of x squared and ln x. You put a raised dot, meaning you are multiplying these two expressions, and we're going to write f times g, and we are going to use the product rule. So y prime is f prime g plus g prime f. So f prime g, the derivative of x squared is 2x times ln x, plus g prime f, the derivative of ln x is 1 over x times x squared. This is, again, the extent of calculus. Believe it or not, we are done with calculus. To simplify, all you have to do, notice that this goes away, this changes to x. So you have 2x ln x plus x. And to come up with this slope, all you have to do, find m as y prime of 1. Replace the x with 1. So if I replace it with 1, I get 2 times 1 times ln 1 plus 1. Ln 1 is 0, so I get 1. Now, please notice, and that's important, this is not the y-intercept. If it were 0, 1, it would be the y-intercept. In fact, this is the x-intercept. So we will use y minus y1 equals m times x minus x of 1. That means y minus 0 equals 1x minus 1. And of course, this has no bearing. This becomes the same thing. Y equals x minus 1 is the equation of a tangent line. We're going to continue with differentiation. In this case, y is log base 3 of a 1 plus theta ln 3. So let's do that. First, we want to decompose this. There is nothing we can do. It's as simple as it gets. So we start with the simple case of looking at this and say, whatever this one is, 1 over f of x, in this case, 1 over f of theta. So that means this is a function of theta, okay? And so 1 over this expression, according to this, 1 over f of x, that means 1 over 1 plus theta ln 3. So that's the meaning of it. Then we need f prime of x. Look at this one. We want f prime of theta. This one is 0. This one is just ln 3. So f prime of x, which we are going to call it f prime of theta, becomes ln 3, everybody. Then 1 over ln b. 1 over ln 3. So I want to make sure we understand this. This part is this part. F prime is this part. One over ln b is this part. And we are done. We are going to simplify it. Now, this is the extent of the calculus, believe it or not. Obviously, these two cancel each other. We have the first part, and y prime is 1 over 1 plus theta ln 3. That's the final answer, everybody. And again, I want to remind you, we've used that. If you ever forget about this concept, remember by definition, by the change of base formula, this is equal to what? This original expression, log base 3 of 1 plus theta ln 3, is the same as ln of 1 plus theta ln 3 over ln 3. This is by the change of base formula. So that's why it creates this third piece. 1 over ln 3 is by the change of base formula. So what I'm trying to say, even if you don't want to memorize that, you just follow the change of base formula when the base is no longer e. All right, y equals ln of 2 e to the power minus t sine t. Here's an example that I guarantee you, if you try to differentiate without decomposing, it's going to be very difficult, which means you have to flip this over and then differentiate what is left. And it is not going to be easy to get the final answer as we want it. So how do you do that? Cut it into pieces. Using what? Well, use the product rule. ln of this plus ln of this plus ln of the final piece, meaning this is algebra. ln 2 plus ln of e to the power minus t plus ln of sine t. And the first thing you notice, this one, ln of e to the power of minus t, ln of e to the power of x is x. So this piece is simply the exponent, negative t. So change this to negative t. And I hope you recognize this as an easy step. Ln of e to the power of x is x. And you can see this arrow again and the fact that exponential functions and logarithmic functions are inverse functions. So with that being the case, let's differentiate one by one and see how easy it becomes now. ln 2, 0. Why? Because it's a number. Minus t, minus 1. ln of sine t, 1 over sine t times cosine t. Again, you remember we did this already. Cosine over sine is cotangent. So the final answer is y prime is negative 1 plus cotangent t. So it's really simple. And you should remember this, uh, all of these properties to help you with the differentiation. In fact, shortly we're going to look at um, what's called logarithmic differentiation. So this decomposition is important. Y equals the t log base 3 of e to the power of sine t ln 3. Again, we are going to use properties of logs to decompose. What are we going to do? Well, reminding everyone that ln of e to the power of x is x, e to the power of ln x is x, log base b of b to the power of x is x. Those are some properties that we should be very comfortable with. So what do we notice here is that e has exponent sine t times ln 3. So we put the ln 3 first, and we put this in a parentheses. Please understand this part is the same as this part. Why are we doing that? Because e to the power of ln x is x. That means now I'm going to replace e to the power of ln 3 with simply 3. I'm not going to touch anything else, just this one becomes 3. So now what we are looking at is this part. Again, the t is not going anywhere, everybody. Log base 3 of 3 to the power of sine t. I hope you recognize this one following this. So take a look at this one now. Log base b of b to the power of x is x. So log base 3 of 3 to the power of sine t must be sine t. We put the log base 3 of 3 to the power of sine t must be just sine t. However, I give you another step. So bring the sine t in front and then write this one as 1. If that helps to see this, or if you use this one to go from here. So let me recap. I want to make sure you understand the properties I used. Number 1, from here, I interchange these two, and I recognize this part as 3. Number 2, I have 2 ways to go. I can put the sine t in front, and then log 3 of base 3 is 1. Or right from here, if I use this property, I can see the answer right here. So I don't even need this one. But I wanted to show you 2 different ways. The reason I want to emphasize the importance of knowing various um, properties. They are truly helpful. And now we are ready to finish the job. So we use the product rule. F prime g plus g prime f. F prime is 1 times sine t. Remember, when you have t, t is the independent variable and you don't have any other variable. Okay. And then sine gives you cosine t times t. You just rewrite it by this one getting rid of the 1, this one putting the t in front. And the final answer, y prime, is sine t plus t cosine t. That's all there is to it. A quick recap. When we want to simplify this, there are two different ways. The first one, of course, we put the ln 3 instead of sine t. This results in 3, and you get here. From here, you can directly to here using this. Or bring the sine t in front, make it a coefficient of log, and that part remains log 3 base 3 equals 1. You should know that, right? Log b base b is 1. When the argument and the base are the same, the answer is 1. And that's exactly what happens here. And you can get rid of it because 1 is an identity element of multiplication. Now, with this in mind, we discuss logarithmic differentiation. This is extremely important because when the function is very complicated, such as this one, the best way is to use logarithmic differentiation. So when the question is asking you to do that, any other method is unacceptable. So you want to pay attention. What is logarithmic differentiation? Number one, take natural log of both sides. So when you take natural log of this, of course, this is ln y, this cuts into pieces. And I'm assuming you have no problem with these properties. So ln of this piece plus ln of this piece minus ln of this piece. And of course, this is x squared plus 1 to the power of 1/2. So one more time. You're going to take the natural log of this. When you take the natural, let me write it down. So we have ln of the left, ln of the right. This one, you have to cut it into pieces. Ln of this piece plus ln of this piece minus ln of this piece. And this one, we're going to write it as x squared plus 1 to the power of 1/2. That's why we have. We are not done. We are going to continue simplification of a log, complete decomposition. 3/4 sits in front, 1/2 sits in front, 5 sits in front. So ln y becomes 3/4 of ln x plus 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. So that is completely decomposed, everybody. Now we are ready to differentiate implicitly with respect to the independent variable class. The independent variable in this case is x. So of course this flips over, becomes 1 over y. But remember, y is like g of x. So think of this one. How do you differentiate this? 1 over g of x times g prime of x. So 1 over y dy dx. 1 over y dy dx of y prime. Sometimes it's easier to write y prime. On purpose, in this question, I'm writing dy dx. I want to emphasize that x is the independent variable, and it may not be. So what is this one? 3/4 times what? 1 over x. 3/4 times 1 over x. What about this one? 1/2 times 1 over x squared plus 1 times its derivative 2x minus 5 times flip this over, 1 over 3x plus 2 times its derivative, number 3. Solve for dy dx, and this is done right here as far as calculus is concerned. So to solve for dy dx, here's what you do. First of all, this is 3 over 4x. This one, so this one is 3 over 4x. What about this one? This 2 cancels out this 2, so we have x over x squared plus 1. And I hope you see that minus 5 and 3 would be minus 15 over the same denominator, 3x plus 2. So that's what it is. And you take the y to the other side and you multiply by it. So one more time, a quick recap. This one is 3 over 4x. This one is x over x squared plus 1. This one is minus 15 over 3x plus 2. And then this 1 over y goes to the other side, becomes y. Must replace it with the y in the first place. Do you have to combine those? Most of the time you don't have to. Sometimes they may expect. And this is as difficult as it gets, but it has got to do with understanding the composition of logarithmic expressions. Now, y equals x to the power of sine x. They're asking for logarithmic differentiation when it comes to a function that has an exponent, which is a function. So the base and the exponent are both functions of, let's say in this case, of course, x or any independent variable. The methodology is to use logarithmic differentiation first. So logarithmic differentiation, you start taking the natural log of both sides. Ln of the left equals ln of the right. So what is ln of x to the power of sine x? Sine x is the exponent. We use the power rule, and the power sine x becomes the coefficient. So now we have sine x times ln x, and we can differentiate both sides implicitly with respect to the independent variable. It happened to be x. So that's the key, independent variable, whatever it is. So ln y is always 1 over y times y prime, everybody. 1 over y times y prime. It is always the case. What about this one? I'm going to write it f times g, f times g, and we are going to use the product rule on that, which means the derivative of f prime g plus g prime f. F prime is cosine x times g ln x plus g prime, the derivative of ln x is 1 over x, times f sine x. And of course, we are going to solve for dy dx or y prime. Again, this is, believe it or not, the only calculus step. So we are going to multiply the y by the right side. So the right side is just cosine x ln x plus 1 over x sine x and times y. And now replace the y with x to the power of sine x. So y prime is x to the power of sine x times cosine x ln x plus 1 over x sine x as the final answer, everybody. There is a different way. I quickly mention it. The second method is we know e to the power of ln x is x. So y is x to the power of sine x, or we can write we are going to replace the x with e to the power of ln x. Now you have e to the power of ln x times sine x, and this one, because the exponent is e, you know how to differentiate. I highly recommend you try that, okay? E to the power of some function, f of x, okay? You know the derivative is e to the power of f of x times f prime of x. So you have to differentiate that. And as you know, if you look at this one, if you look at this part, it's identical with what we got here, class, in a different order, but it's the product rule that says order is not important. So ln x times x or sine x times ln x, we basically differentiated this. So you get this one. So you have to differentiate this. Okay, remember that. And then times itself times this piece. And what is this piece? Go back and put x sine x. So that's another way of doing it, just in case. But if the question asks for logarithmic differentiation, this method is not acceptable, okay? Derivatives of inverse function. We're going to go over them, and then I'm going to look at some of the proofs. When we have sine inverse, tan inverse, and secant inverse, the derivative of sine inverse is 1 over 1 minus x squared, square root of 1 minus x squared. The derivative of tan inverse is 1 over 1 plus x squared, and the derivative of secant inverse x is 1 over x times square root of x squared minus 1. Now, what about cosine inverse? The same thing, negative. Cotangent inverse, the same thing, negative. Cosecant, the same thing, negative. So notice, instead of 1, for all of this, we're going to use minus 1. So it's easy to memorize them. So stick with those. As long as you remember them, the rest of them, you just negate them. That's all. Also, I remind you, when we say sine inverse of x is y, that by definition of inverse function is sine y equals x. And remember, this works when we did the restriction on the domain of sine from minus power to pi over 2, then it was 1 to 1. And it created a situation to come up with an inverse. And now y has the limitation from minus power to power 2. And so, reminding you, sine inverse of sine is x if x is between these two numbers. Remember the restriction we put. Sine of sine inverse of x is x. Remember, both of them means f of f inverse equals x. Two function, their composite function is x if they are inverse functions. In this case, it works if this x is between -1 and 1, because this x refers to the range of sine. Okay, remember the range of sine is from -1 to 1. Same concept with the cosine. Cosine inverse of cosine is x. If x is between 0 and pi, remember the restriction we put for cosine was different from 0 to pi. In other words, for sine is the fourth and first quadrant. In this one is first and second quadrant, and cosine of inverse becomes x. Again, if x is between -1 and 1. So to recap, we put all of them here. What I'm adding, okay, so this stuff, but I'm adding, what if we, instead of sine inverse we have of x, we have sine inverse of u, the numerator becomes du dx and the x changes to u. That's why we put 1 here, because the derivative of x is 1, everybody. The derivative of x is 1. But if it's a function of x, then you need the derivative here. So u is a function of x. You need the derivative here, and you need the u here. Now, instead of u, I'm going to put g of x. Again, two different formats just to you see what happens. So it's the same as that one in essence, remember du dx or g prime of x means the same thing because this is really u. So 1 plus g of x to the power of 2, that would be the denominator. The numerator, instead of 1, becomes g prime of x. So I hope it's clear to everybody. So we can move on. All right, let's look at the following derivatives of inverse functions. We have them here. Sine inverse of x equals y. That means sine y equals x. Y is between negative power 2 and power 2. The derivative of sine inverse of x is 1 over square root of 1 minus x squared. That's what we have mentioned. Let's look at the proof. To prove that, remember when sine inverse of x equals y, that means sine y equals x. In other words, I'm repeating this statement, everybody, this one. This is just being repeated here, nothing brand new. And again, this has got to do with understanding the concept of inverse functions, everybody. Now, let's differentiate this expression. So let me erase everything. This one, let's differentiate both sides with respect to x. And I start with the right side because we know the derivative of x is 1. And this one, we do it implicitly. What is the derivative of sine y, cosine y, dy dx? And that's the idea. I hope everybody's comfortable with that. So what is dy dx? 1 over cosine y. But the question is, what is cosine y? Well, you know, sine squared plus cosine squared is 1 of the Pythagorean identities, which makes cosine squared is plus minus. No, cosine. Cosine theta plus minus 1 minus sine squared theta. Same thing happens here. Cosine y is plus minus square root of 1 minus sine squared y, but cosine is positive from negative power 2 to power 2 in the fourth quadrant and the first quadrant, so it's only positive. And sine y is x. We are going to replace this with x. So we are going to write equals 1 minus x squared. So now we are going to replace the cosine y, and we get exactly what we were claiming. So we proved the first one, everybody. Of course, in the same manner, you can prove the rest of it. So I'm showing you one proof to indicate it's really not too bad. We can prove all of them. We are going to move on. Now let's discuss tan inverse. As far as tan inverse is concerned, if we write tan inverse of x equals y, it means tan y equals x. And I hope you remember, we basically use the same restriction as we did for sine, except the endpoints can't be included. And now we are saying the derivative of tan inverse must be 1 over 1 plus x squared. So we are going to look at that one. We are going to prove that one. So, class, we are working on this. I mean, this one. Let's just erase this. We are going to differentiate this. Again, I start with the right, x is 1. The right side, as you know, the derivative of tangent is secant squared. So secant squared of what? Whatever the variable is, secant squared of y. And because it's a function of x, let's say secant squared of g of x. So g prime of x or dy dx. This is implicit differentiation, everybody. So if we divide by secant squared, the x becomes 1 over secant squared y. We remember the Pythagorean identity, 1 plus tan squared is secant squared y. So tan y is x, so we are going to say 1 plus x squared is secant squared y. So we can replace the secant squared with 1 plus x squared, and therefore we proved the derivative of tan inverse of x is 1 over 1 plus x squared. Again, as we did with trigonometric functions, we proved a few of them, and I highly recommend you prove the rest of them as well, just for practice, everybody. That is truly helpful if you can do that. It helps you with your techniques of differentiation. Now let's differentiate y equals e to the power of 10x times tan inverse of x, and I'm going to put f g, meaning we have to use the product rule on this. F prime, what is the derivative of e to the power of tan x? So we're going to write y prime is e to the power of tan x itself times the 10. This is the derivative of the first piece. So this entire thing is f prime times g, tan inverse of x. Plus, now tan inverse of x, we know it's 1 over 1 plus x squared. So that means you're using this one. 1 over 1 plus x squared and times e to the power of 10x. This is g prime f e to the power of 10x. So I'm going to write at top of it, everybody, f prime g plus g prime f. And we rewrite this simply by putting the 10 in front. There's really not much we can do, and put the e at top of this fraction. And we have the following, everyone. Y prime is 10 e to the power of 10x, tan inverse of x plus e to the power of 10x over 1 plus x squared. That's the final answer. So it's pretty straightforward, everybody. Y equals cosecant inverse of e to the power of x. So please understand this is g of x or u. So we are going to look at cosecant inverse of x, and then from cosecant inverse of x, we should be able to come up with cosecant inverse of u or g of x first, and then we work on this piece. So notice that cosecant inverse of x is negative 1 over x squared of x squared minus 1. So this x is the same. That means if you use u, this is u, and this is u squared. Negative 1 is negative du dx. If you call the u g of x, then that means negative 1 over g of x times square root of g of x quantity squared minus 1 times g prime of x. Again, this is the chain rule, everybody. So let's follow that. Negative 1 over something square root of something squared minus 1. What is that? That's g of x. So your g of x is e to the power of x, which means you are going to replace this one by e to the power of x, replace this one by the same thing, g of x or e to the power of x. Then you need g prime, everybody. Now, what is the derivative of g of x or e to the power of x? Happen to be itself. It just happened to be itself. It's not always the case. This happened to be itself, which means now this cancels out this one in this particular case. So you're left with this one, negative 1 over the square root of e to the power of 2x minus 1. Again, normally it doesn't happen this way. It happened here simply because the derivative of the function g of x when it's e to the power of x is itself, everybody. Just a quick recap to make sure we understand what's going on. Cosecant inverse, we said the derivative is minus 1, x squared of x squared minus 1. So we write the same concept, but it's not x, it's a function of x, g of x. So we follow this format, and minus 1 over g of x times square root of g of x quantity squared minus 1. So e to the power of x, e to the power of x to the power of 2. And then g prime, this is by the chain rule, the derivative of e to the power of x is itself. These two cancel each other, and this means e to the power of 2x. So we write minus 1 over the square root of e to the power of 2x minus 1. Y equals x sine inverse of 3x, and this is the product rule, everybody, because this is f times g. We need f prime g plus g prime f. So what is f? What is f prime is 1 times g sine inverse of 3x. Plus, what is g prime? Now let's discuss the g prime. So we know the derivative of sine inverse of x, and also I discussed when it's not x. It's 1 over square root of 1 minus x squared. Therefore, the derivative of sine inverse of u, it's du dx over square root of 1 minus u squared. Or you can say the derivative of sine inverse of g of x is 1 over square root of 1 minus g of x times g prime of x. So the way we are going to write it, we are going to write it in this fashion, and we're going to leave this empty. So we keep the 1 and 1, and we leave this one empty. So this one is g of x, therefore you put 3x, and this one is g prime of x, which is 3. So you put 3x here. This one is times g prime of x. Rather than writing it here, I put it there, and times x, which is f. So I'm going to write at top of this f prime g plus g prime f. A quick recap, x gives you 1, sine inverse of x, and this one, you put 1 over the square root of 1 minus something squared. What is squared? That's the g function. What goes up here or times that is the derivative of that, which is 3, and then this is fx. So this is simply sine inverse of 3x. This is 3x minus, okay, plus, my apologies, it's hard to see that, I shouldn't have crossed. So plus, and then 3 square root of 1 minus 9x squared, that's the final answer. Why is x cosine inverse of x minus the square root of 1 minus x squared? So we need to differentiate this, and we recognize a couple of things. Number one, this is 1 minus x squared to the power of 1 half, and the reason we write it in this format so it becomes easy to differentiate. Then this is the product of x and cosine inverse. So it requires the product rule again. So we're going to do the product rule on this one. X is 1 times cosine inverse, the g, plus g prime. Now the derivative of cosine inverse is the same as sine inverse, but negative. So negative 1 over square root of 1 minus x squared. Times f, which is x. So that part is done. We're going to work with this minus, and we're going to differentiate that, minus 1 half, same thing to the power of negative 1 half. 1 half minus 1 is negative 1 half, times the derivative of the inside, which is negative 2x. And I'm going to put an asterisk next to it because that's it. As far as the calculus is concerned, we are done. We are going to do algebra to finish it. I'm going to recap before we do so. This part requires the product rule f prime g plus g prime f. F prime is 1 times g is cosine inverse. G prime is negative 1 squared up over the square root of 1 minus x squared times x, which is f. And this part uses the extended power rule, 1 half times 1 minus x squared to the power of negative 1 half times negative 2x. So this is cosine inverse. What is this one? Minus x over the square root of 1 minus x. I want to make sure we understand this. So first of all, this 1 half and these two cancel each other. This negative and this negative give us plus x, and this one goes down and take a positive exponent, which is the square root. So this is cosine inverse. This is the same, but with this x becomes minus x over square root of 1 minus x squared, and this is the same thing but positive. Therefore, these two cancel each other, and the final answer is simply cosine dy dx is cosine inverse x. That's the final answer.